you very much.
It's laser cooling of barium monofluoride.
Yeah, thanks again. So let me also start by thanking the organizers first for giving me the opportunity to talk about these slightly weird molecules, as you will see. So that's barium monofluoride, which is one of the experiments in my group. So let's maybe start with the general question, why would you even want to do that? And so it turns out it's actually quite a rich molecule in a sense, because there are many isotopes of barium. And so you actually get many different kinds of barium monofluoride isotopologues. There's most prominently, I come from atomic physics, so for me it's just bosons. Maybe for some of you, we like to talk more of even isotopologues, and the most abundant one is 138 barium fluoride. There are a bunch of others as well. And then there are also our little fermions, the most abundant one, 137 barium fluoride. Now, I'm very happy that Mike already gave a nice introduction about all of this. So these ones here, the bosons, they're also candidates for EDM searches. And there's actually a large number of groups working on this already. And the story is basically the same as what Mike was telling you. There's a valence electron sitting here somewhere which experiences a huge effective electric field. The one in barium fluoride is actually, for the experts, not quite as large as in other species. But the idea is that this molecule is slightly lighter than thorium oxide or YDF, for example, and it could maybe easier improve experiments through cooling and trapping of this molecule. We will see about this. There are also a number of experiments that try to implant these molecules into crystals. And for that, you need beam deflection. So even if laser cooling doesn't work, it's still useful to manipulate the molecules. On the other hand, for these odd isotopologues, the main application is parity violation. And here the idea is that molecules give you states of opposite parity that are closely spaced. And if you put this molecule in a magnetic field, you can even enhance your sensitivity further to things like anapole moments or generally weak effects in the nucleus, and learn something about it. And you see already the abundance is quite significantly lower than for the bosons. And so here the challenge is really first to accumulate molecules in the first place so that you can do these measurements. Now, for these molecules here, the laser cooling, in principle at least, is relatively straightforward because the structure is very similar to molecules that you may have heard about already, like calcium fluoride and strontium fluoride, but it has not been fully demonstrated yet for this species. Here, you actually get two nuclear spins, which complicates things quite significantly because you get resolved hyperfine structure that you need to deal with, and then you need to come up with very new laser cooling strategies. And I will try to talk about progress in both of these directions during my talk. Just to put this all into perspective, I always like to steal a plot from Stefan, which is a very nice plot, which gives you an overview about all the diatomic molecules, at least, that people have considered for laser cooling. And what you see here on the axis, the acceleration that you can achieve and the recoil velocity that you can transfer. So let me translate this maybe a little bit. This tells you how strong the forces are, and this is for how long you can apply the forces. So essentially, the more you go into this corner of this plot, things become more difficult. And barium fluoride is right here. So, but as Mike was already pointing out, this is a price you have to pay because it's mainly related to the mass of the molecule. And of course, the heavy mass makes this corner of the plot interesting for precision measurements. Now, Stefan will later tell you that, of course, you want to be up here on this side of the plot. And these are, in principle, easier to cool, these molecules, but then you have to deal with more challenging laser technology. So there seems to be a sweet spot in between, which is also mainly calcium fluoride these days, and you will hear a lot about this. We also have an experiment working on this in Stuttgart, but I will focus on the barium fluoride for today. So this is something for another day. So then let's get started, and let's start with the most abundant bosonic isotopologue, which is rather simple. And just as in Mike's talk, we use laser ablation and buffer gas cooling to generate these molecules. All very straightforward, and it turns out it works quite well for this species as well. We ablate solid precursors, and then they thermalize to around 3 Kelvin because we pump on a helium cryostat. So we get an internally cold beam, and we also get a slow beam. So nothing too special about that yet. Now, in terms of the laser cooling, it's also, like I said, a thing that relies on diagonal Frank-Condon factors, and barium fluoride is one of these typical species which have an alkaline earth and a fluorine atom, and so they share one of the electrons of the alkaline earth atom, and the other one is sort of located away from the bond, and so it doesn't care too much about the excitations that you get, and so this whole list of possibilities has been studied for these type of molecules already. I mean, we don't have to talk about calcium and strontium fluoride, which are of course very well established, but people are considering magnesium fluoride as well. Beryllium fluoride at least has been discussed in theory. Radium fluoride, as you know, there has been extensive spectroscopy these days. And now there's a lot of groups working on barium fluoride, and I want to advertise the talk on Friday by Roman Bause from Groningen also, who are also working on this. So now, to realize the cycle, as I said, it's relatively straightforward. The level structure is pretty much the same as in the other laser coolable species with reasonably diagonal Frank-Condon factors, and actually for this species, very convenient wavelengths that are close to the D1 and D2 transition of cesium, so you get a lot of laser power almost for free. Also, the hyperfine structure in the ground set is almost equidistant, so you just put a simple EOM and you get all your sidebands. Seems very simple, and you can indeed realize optical cycling in the beam very easily with this. And you see this is the fluorescence of our beam. As we turn on a magnetic field and remix dark states, fluorescence goes up. So cycling works. Here we're scattering about 10 photons. There's a few caveats though. In this species, I have not told you that there's also an intermediate electronic state here, just like in YDF, which was a big problem also for YO in June year's group. Then we're still located in that bottom left corner of the plot on the slide before. And so there's very small recoil, a high mass, and a low scattering rate in this molecule, unfortunately. And so if you put in the numbers, it turns out just for transverse cooling, you need about a 30 centimeter region. So this is what we had to build. So here's the experiment with the buffer gas source on the left. And then there's this region here, which is 30 centimeters long indeed, where we bounce back and forth laser beams to realize laser cooling. And then in the end, here there's room for experiments, which I'm not going to talk about this, but of course you can imagine your favorite precision measurement interaction region here. Turns out, even though this molecule is very heavy, there's also prospects for slowing it down using more sophisticated slowing techniques. But again, this is something for the future. So for now, here we can take a picture of our barium fluoride beam. And when we did this, of course, then you want to start cycling in your laser cooling region, but we found there was only very slow cycling, much slower than you would expect from what I've told you so far. And so the question was, what is the problem? And it turns out, on top of the complications that already come with the properties of this molecule, it turns out there were things that we didn't know. The first one being this hyperfine structure here. You see in all the molecules like calcium fluoride and strontium fluoride, the excited state is normally not resolved. And so it's a relatively simple structure, but it turns out if you do Doppler-free absorption spectroscopy, you find out essentially this excited state is split. And it's well resolved, which has also been measured in other groups, but it makes it different from the regular species like calcium fluoride and strontium fluoride. And if you plug now these numbers into simulations for your cooling forces, it turns out if you just go ahead and address these ground states as you would normally do, in theory, you get a nice force. But that is if you're ignorant of this excited state. If you now plug in the resolved excited state, then all your forces basically disappear. They become much lower and also active over much smaller regions. So there's essentially nothing happening anymore. So you have to take this into account. This can be done, for example, been demonstrated recently in Boyan's group, that you can create Doppler forces. I'm saying specifically forces, not yet cooling here, because you see along the way they're actually losing 75% of their molecules. And that is also a very common problem in a species that has not been laser cooled before. You have to find your repumping transitions. And that is usually very challenging because they're very weak. And here the large mass seems to help us a little bit because the vibrations in our buffer gas cell, they thermalize very, very poorly. And that gives us a way of actually doing the spectroscopy on all these different vibrational transitions right in the buffer gas cell. And it turns out in barium fluoride, there's a lot of perturbation because there's a lot of close-lying excited states that shift these states around, and that basically results in the old spectroscopy being significantly off. So we had to redo all of this. and look at it in detail. So here's just one example. I don't want to bore you too much with spectroscopy, but there's a few nice things that you can learn from this. First of all, you can see that we are, well, not yet, but in a second, see that we can actually work with all our isotopologues that we have in this species. Yeah? So these big peaks here, that's the 138, the most abundant one. This is the laser cooling transition here. There's 136, which you can also still see in a very straightforward way. So we were able to extract new sets of constants for all of this. And then there's also these odd isotopologues, which you see don't really fit here very well. And the analysis for this is still ongoing. And it turns out for these also, the excited state hyperfine structure was completely off. And it's very hard to assign because there's hundreds of lines. And turns out you will hear on Friday from Yuli a talk on how to calculate the structure of these molecules. I don't think she's going to talk specifically about this topic, but they helped us basically to extract constants which now allow us to also understand what's going on in these fermions or odd isotopologues. And also assign actually more less abundant isotopologues. Because now with this, actually, besides the practical interest in laser cooling, you can play around already a little bit. It turns out there's this way of analyzing isotope shifts in atoms, king plot analysis. Basically, isotope shifts are linear, and you can play the same trick with molecules. So your isotope shift here is proportional to a field shift, which is actually proportional to the nuclear charge radius of your atom inside your molecule. And then there's a mass shift, which is just a normal thing that you learn about in your atomic physics class. And it turns out these isotope shifts are very nicely linear still in these molecules. And it turns also out that these shift constants here, they change with the transition you're addressing. And that is actually a nice benchmark for structure calculations if you want to calculate this on a quantum chemistry level. What you can also do is you can do a little bit of nuclear physics already, just on this very basic level, and calculate back to the nuclear charge radius, which you can now extract from molecular spectroscopy to extract here for the barium nucleus, the radius of that nucleus. And you see, of course, it increases with isotope number, but on top of this, there's this odd effect that there's this even odd staggering in the size between even and odd isotopologues, isotopes in this case, sorry, of the atoms. Yeah? And so, first of all, this is very useful to validate spectroscopy, in particular for these very low abundant isotopes here. But it's, of course, and that's the general idea behind this, attractive for atoms that you cannot get in an atomic form very easily. When you create exotic nuclei, they often form molecules, actually. And so you can do spectroscopy on the molecules now and extract nuclear properties from this. And of course, as Mike was showing you, these vibrational transitions, they can, of course, be measured also with much higher accuracy. So eventually, you can consider this to be competitive with atomic spectroscopy. Now, then another thing that we can use this for is a nearly background-free detection of our molecules. So precision experiments obviously rely on counting molecules in the end. And so scattered light is always a problem. So if we put our molecular beam into a glass cell and do the normal optical cycling here, we don't see anything. The camera is completely saturated. But then you can also create a closed optical cycling by using what we normally use as a repumper here, and then a so-called depumper, and then the fluorescence will be Raman shifted. Yeah? And with this, you very nicely see a molecular beam right away, even in an uncoated glass cell. So this really improves the signal-to-noise ratio significantly. I will come back to this in the end of my talk because it's very useful for the less abundant isotopologues. So then you need to optimize your cooling forces. And now with this level scheme, there comes a problem. You don't know, do I red detune, do I blue detune? Where do I put my transitions? Because if you blue detune for one transition, you red detune for the others. And again, your forces are not very nice for laser cooling. And so it turns out actually for these more complex structures, you can use less laser frequencies that do not address every transition, but you just address the strongest ones. And that actually only slightly decreases your Doppler forces, and it may even increase your sub-Doppler forces because, I mean, these are all lambda level schemes, and you always have some dirty resonances in there, and if you reduce the frequency components, actually the forces become larger sometimes, if you do it well. And that's actually a general strategy. So just address the strongest transition and drive the other ones off resonantly. And that actually unlocks a lot of molecules with very complex hyperfine structure. I will talk about our complex fermions in a second, but also, for example, the radioactive molecules that everyone is talking about now. You will have to use approaches like this. And then so with this knowledge, we can proceed towards transverse cooling of our beam. Yeah, here's the setup, very similar to what Mike was showing you. There's one more caveat though. The line width is so narrow, you have to really take care of the frequency of your lasers if you want to see laser cooling. And on top of this, because it's so narrow, you have to very precisely align your molecular beam, because already 1 degree misalignment, and the people working on molecular beams will know you can easily get 1 degree off, means you already have 2 line widths Doppler shift. So then your forces are gone again. But yeah, we managed to set this up. We create our sidebands by some special techniques. And then we can interact over the whole 30 centimeter region, pump into a higher state, and really scatter hundreds of photons now in these heavy molecules. And here's some very preliminary data where we see the typical behavior as a function of detuning of our beam. That the beam becomes smaller and larger depending on whether we're blue detuned or red detuned, so heating or cooling. What you actually also see that in the profiles, there's not much of a change, and that's something you would expect for heavy molecules because Doppler cooling is really not necessarily what you want to do. So the pictures that Mike was actually showing you, that was Sisyphus cooling, which is very effective in these systems. It's harder to set up over 30 centimeters, so that's why we started with Doppler cooling. And here's a simulation, and you see there's very similar behavior to what Mike was showing in YDF. So this is what we're working on now to apply this also here to our molecular beam and really accumulate a lot of these barium fluoride molecules. So let me now switch gears and go to the more complex fermionic ones. So as I said, the problem here is that you have 2 nuclear spins. That gives you a very complex hyperfine structure here that you need to deal with now. What is actually very nice in barium fluoride is this rotational cycle that you normally use is still a very good one. So you don't get a lot of leakage out of this. So in principle, you should be able to cycle a lot of photons if you just find a way to deal with the hyperfine structure. And so just to give you the number per vibrational level, it's 48 and 16 levels. And then you need to apply this to 3 or 4 vibrational levels in the end. But it turns out you can use exactly this strategy that I was telling you about before. You just drive the strongest transitions, and the other ones, you just drive them off resonantly. And that gives you actually reasonable cooling forces. And you can put this into a simulation, addressing, again, only these 7 transitions. So this is now using 4 lasers and 112 levels, which is very reasonable. And so you have your normal diverging molecular beam. And for the measurements that you want to do with this species, the parity violation measurements, I said you want to put this into a magnet. And these magnets are usually very long. And so behind these magnets, normally there's not much signal left, unfortunately. But now if you apply laser cooling, based on these simulations, you can really enhance the number of molecules by a factor of 10 to the 4 behind this magnet, at least in simulation. Maybe it ends up being a factor of 300. Like in YDF, but it's still very significant and will very significantly improve the sensitivity for parity violating effects. Now, but you may ask me, of course, Tim, is this even reasonable to work with these low abundance isotopologues if the bosonic highly abundant one is already very hard? So here's a summary again of the abundances that we have. So the fermions that we're interested in would be these 2. So you see about a factor of 10 lower than for the bosons. So I'm not going to show you anything for the fermions yet, but what we can of course do as a testing ground is just work with the 136 boson, which should have a very similar structure to the 138, and it's just characterized. So again, this is a factor of 10 lower in signal. And one thing I would like you to take home with about this is that, of course, if you do now laser cooling of different isotopologues, you need to navigate the spectra, and they may be very, very busy. So if you just look at the cooling transition, just purely electronic transition, it's still fine. So if you just want to cycle, this was recently, for example, demonstrated in YDOH, it's basically textbook what you learn from atomic physics. The transitions are just shifted, no problem. But if you look at, for example, repumpers, so this is the P branch, and n equal to 1 is the normal laser cooling transition. Then in 136, this actually gets shifted in this direction. And for example, here we're overlapping with the n equal to 5 transition. So things become quite busy. So there's overlap with higher order transitions. For Raman imaging, where we're going the other direction through the vibrations, then you suddenly get shifted into the Q branch of the more abundant molecule. So if you really want to say, you're working with the lower abundance isotopologues, you have to be extremely careful here. It turns out to work well for barium fluoride. I'm actually simplifying this here quite a bit because there's a lot of other lines from the fermions in there also. But for example, if you think about cooling, the strategy is normally you crank up your laser power as much as you can to get the largest forces, but this is something you cannot necessarily do because then you will start to overlap with the other species. So you have to be a bit careful, but as I said, it works out fine. So we can basically use the same setup as before now, create the molecules, and then have a first photodiodes here and look at magnetic remixing. And yes, we can cycle in 136 barium fluoride. We can also see this now here in our experiment or detection region. We get a signal, and now in the cooling region, if we turn on the cooler for this, we pump all of these away. And if we turn on the repumper, we get them back. So that seems to work very well. So here we're scattering about 200 photons already. Everything from the other species that may be happening in here, it just scatters one photon and they're gone. So we're really accumulating molecules now of that isotopologue. And again, because we have this low noise detection, we can take very nice pictures here as well. So here, I mean, just the cell wasn't very clean. We just tried this, and the beam was a little bit faster, which is why this is only 200 photons. But in principle, we should be able, if we can cool 138 barium fluoride, we can also cool 136. And actually now you can play this further. I think 134 should also be very, very feasible. And then the next one is 132 barium fluoride, which only has a fraction of a percent. If that works, then you're already reaching into this regime where all these radioactive species are located. Yeah? So you can really liken at the tool that you have with atoms, where you accumulate rare exotic stuff. That should also work with molecules in a very straightforward way. Good. Then in my abstract, I actually promised also to talk a little bit about many-body physics, but I will only give you one slide. In Stuttgart, we like to work with these monoatomic molecules, with these dysprosium atoms, which have large dipole moments. And you've heard already yesterday that we discovered this weird state, supersolid, that is both superfluid and crystalline at the same time. And along the way, and that's actually the take-home message that I want to present, is that there's a lot of new tools that have been developed in dipolar physics, both on the experimental and on the theoretical side over the last years, based on these monoatomic molecules. And this can be applied directly to the real molecules that we've heard about, for example, yesterday. Yeah? And we've tried to do this on the theory side already a little bit. You've seen this plot already yesterday. There are these weird states where a normal BC turns into these weird patterns, and so on, and we've really calculated this is very, very feasible once there is a molecular PEC. So very strong motivation to realize this. And also, if you load these molecules into lattices, we've also heard about this yesterday, also very reasonable parameters to realize all of this with these laser-cooled molecules. So if you're interested about this, talk to me later. I also want to advertise a review that we recently wrote, if you're interested into all of these techniques. Giacomo is somewhere back there, and Jun and Bajun, which should give an insight in both association of molecules and laser cooling. And then I also want to advertise we're actually moving to Vienna. So we have, as everyone, a lot of open positions. And I just want to point out, if you want to live in a nice city, Vienna is a good choice. But, the most livable city, not only once, but for the last 10 years. So that brings me to my summary. I've talked about barium fluoride, which is a challenging molecular species. I think I've convinced you of this, but cooling is really making progress. This cooling should really work for different isotopologues of this species, which is one of the selling points for this. And there are also many exciting prospects for, let's say, more accessible ultra-cold calcium fluoride or dipolar dysprosium atoms. Here's the people who did all this, and that brings me to my end, and I thank you for your attention.
Questions?
Let me ask about your one-atom molecule. So you were saying that maybe we could learn from one system and transfer to the other. Obviously, they have the same sort of dipolar interactions, but What about the short range stuff? I think in dysprosium you can maybe treat the short range part as a contact interaction. I don't know how clear it is you can do that with
Yes.
molecules. Do you have any insights or
Yeah,
thoughts
so
on this?
you're absolutely right. I mean, we've learned yesterday that the shielding for the microwave shielded molecule sits at 1,000 A naught. But it's not very short range anymore. And so these methods will need to be adapted. That's what we're doing right now. But of course, different dipoles, it turns out, they give you very, very different new effects that you cannot explore with these atoms. But the tools that have been developed for these atoms, they have not been applied to the molecules. And so there's a lot of work to do on the theory side, which we're trying. And then, of course, everyone is trying to get them cold and do it in the experiment.
Why is the subdoppler cooling harder than the Doppler cooling over 30 centimeters?
Oh, because it's just terribly hard to align the laser beams. And for the subdoppler cooling, you need them from two directions, right? And so then overlapping all of this is just, it's a pain. It's just technical reasons. So we first tried to align one beam, which was hard enough to do it like straight and align it also with a molecular beam that you obviously don't see. And so subdoppler cooling is just more laser power, more alignment.
Any other questions?
I was thinking about the parity violation experiments. You need this large magnetic field, a very uniform magnetic field. Did you ever think about molecular ions in a penning trap?
I did not, but I believe there was a proposal at some point. I have to check. I'm not entirely sure, but there may be.
It's like a fairly natural way to do it because you get your big and uniform magnetic field.
Yeah, I don't know though how precisely they can control this magnetic field. I mean, it's just very large, but I'm not sure it's very homogeneous with all the other electrodes around.
So it can be.
So, can I ask
see a
you,
question.
how do you, okay, so after the laser ablation, how do you make a molecular beam to the magneto-optical trap? Like, how do you make a beam?
So there's simply a hole in the cell. So the cell is this enclosed volume, chunk of copper with a few holes drilled in there. And then there's one particular hole that we leave open, and that's where the molecular beam moves out.
But after the ablation, there should be plasmas, right? Some sort of plasma, but you need a beam for cooling.
Yes, so there's helium inside this buffer gas cell. That's the coolant, and that just flows out and washes the molecules out. No, it's just a helium gas. Yeah, that's it's just there. You need to pump it away.
So in the interest of this being recorded, it would be fantastic if you used your microphone for asking questions, because otherwise it won't be recorded. Anyway, are there any other questions? Last question.
So you mentioned that you can use biochromatic force to decelerate molecules. Can you elaborate more on that? Have you tried that?
We have not tried it, but we've calculated it already. And so the thing why I say this is very favorable in barium fluoride, people have considered this, for example, for calcium fluoride before, is that we have these very nice transitions where almost infinite laser power is available. And so this makes it very attractive to apply this. And the numbers seem very reasonable.
All right, I think if there aren't any other questions, they will have to wait for lunch. Let us thank the speaker again.